It's been a long time since I've done this. So let's start. Universal gravitation. Yeah, I know all of this stuff. We don't need to do this. Okay, just start. First question, or I should say the 200th question. A planet of mass m moves along a circle around the sun with velocity something equal to okay whatever. Find the period of revolution of this planet around the sun. Okay, they give us the velocity. We're gonna find the period. So time period equals the velocity. Cool. No big deal. Uh, So actually, let's do this thing for elliptical orbits. It's first, instead of doing all of this, we'll just write down some formula that will be useful to us. So in an elliptical orbit, right, something like this. This thing is R minimum, this thing is R maximum, right? At the maximum R value, you will have the maximum, sorry, the minimum V value. And then over here, you're going to have the maximum V value. And then these are all perpendicular because dr upon dt equals 0, right? So for minimum and maximum, dr upon dt equals 0. And yeah, right, this is an ellipse. The semi major axis is small a, so basically like 2a is equal to r minimum plus r maximum, whatever. And for using all that geometry, you can easily write this r minimum is just equal to a times of 1 minus e. This thing is equal to a times of 1 plus e. Okay, the uh, the angle swept in some time t, right? So that is proportional to time t. And what is that rate? So what is dA upon dt? That is just equal to half r vector cross v vector. So use the geometry for the thing and you will get the thing. All right. So we have to figure out what that is. And this is actually going to remain constant because angular momentum conservation. So it's just equal to, and by the way, v min is just equal to square root of gm upon a times 1 minus e upon 1 plus e. And v max is just equal to square root of gm upon a times 1 plus e upon 1 minus e. So if you don't know where this formula come from, go watch that video of mine where I actually do this thing, right? I actually derive all of this. Anyway, what we are interested in just this much. So d upon dt is equal to half r vector plus v vector, right? Yeah, which is just equal to, just wait a second. Right? Hopefully now it will be a little less noisy. Anyway, let's just keep going. So you got half, and just choose one of these. So just say the minimum R value. At that point, you got maximum V value. So it's like a times of 1 minus E. And this times, so not the cross product anymore, just this times this stuff. And by the way, just need the magnitude of this guy because, right? So you want this, right? It's just going to be like square root of all of that. So let's do the thing. Gm upon A times 1 plus E upon 1 minus E. And then you want to do all of this, which is just, you can write this thing as 1 upon 2 square root of gm, and then it will actually square root of gm, and that times a power, what is this? You got, oh yeah, it's supposed to be square root of a in that case, whatever. So square root of a, and then you got this stuff. So 1 plus e and then 1 minus e, right? That's just 1 minus e square, I guess, in the square root. Yes. And the total area is just pi times a times b. So pi times a squared times square root of 1 minus e squared. So when you divide this area upon the area rate, just get the time period. The time period is just, right, so divide this thing, what do you get? You just get like 2 pi upon square root of gm, the constants, and then this one a, okay, it's like e power 3 upon 2, and then this factor cancels. So perfect, right? So you can always use this thing. Okay, that's one of the equations that we'll be using. So t is equal to 2 pi upon square root of gm a power 3 upon 2. So this is completely in terms of, the radius or whatever you want to call it. We would also like this in terms of velocities, right? So you see that you got like v max and v min. What happens if you like multiply these? It's going to be square root of gm upon a squared. So it's gm upon a, right? Yeah, that's what I'm getting at, is that gm upon a is just equal to v min times v max, right? So you can actually write a as gm upon v min times v max. You get the thing, and then just put that in there. So And this thing can be thought of as 8 times square root of a or something like that. Yeah, okay, sure. So putting that, just get like 2 pi gm power 3 upon minus 1 upon which is gm. So 2 pi gm, and then this was upon v min v max. So that power 3 upon 2. So upon v min v max to the power of 3 upon 2. Hopefully it's gonna work out or something. Okay, that is a nice formula we got over there. So right, you will be using this. Okay, that's perfect. You got the time period in different values. Okay. Uh, right. So do we actually need anything? No, actually we don't. We just need v min, v max, these two values which we already know, and then you just take time period. That's it. That's all you need. You don't need anything more than that. These few formula are enough to solve everything that you will come across. I mean, everything related to elliptical orbits, whatever. Let's start now. So 200. A planet of mass m moves along a circle around the sun with velocity v is equal to something related to the helios, whatever. Find the period of revolution of this planet around the sun. So it's a circle, the eccentricity is 0. So v min and v max are the same, which is v. There we go. So it's like 2 pi gm upon v power 3 upon 2. That is the thing. And yeah, okay, 3 upon 2 squared, right? So 3. And we won't calculate what this thing is because we don't know what m is. So yeah, this should do it. Next, 201. The Jupiter's period of revolution around the Sun is 12 times that of Earth. Assuming the planetary orbits to be circular, find how many times the distance between the Jupiter and the Sun exceeds that between. So they gave us what? So Jupiter's period of revolution, right? So do the thing. So Jupiter, and then you got the Earth. So the time period of revolution. This is in what ratio? So it's 12 times that of the Earth. So it's 12 is to 1. Okay. What about the E values? So, and these are like circular orbits or something? So these are circular, then A is just equal to R. And we know the thing, T is just equal to A power 3 upon 2. So like 2 power, yeah, okay, power 2/3 of T. That's what the proportionality is, right? So 12 power 2/3 is to 1. Okay. And also for the speeds, right? That's also what you want to find. Velocity and the acceleration as well. Okay, cool. Acceleration is just, it's a 1 upon r squared. So that works out. Cool. Uh, yeah, I mean, should we actually, that's in terms of acceleration? Not really. We don't want to be doing that. Just no point in doing it. Okay. So what is V? Yeah, okay, you got the T stuff, and then yeah, it's gonna be like V cube. So V cube proportional to 1 upon T, V proportional to 1 upon T power 1/3. So you got right, 1 is to 12 power 1/3. And the acceleration is like 1 upon r squared. So you got 1 and then 12 power 4/3. This table is enough. Okay. So A, how many times the distance between the Jupiter and the Sun exceeds that between? So how many times? So you mean like a factor, right? So you want R Jupiter upon R Earth, right? So A is pretty easy. A is just 12 power 2/3. What about B? And the velocity and the acceleration of Jupiter in the heliocentric reference frame. So you got the velocity, no big deal. Oh, okay, this is going to be a big deal because, right, okay, this is kind of, so you got 1 upon 12 or 1/3, but that times the velocity of Earth, we don't know what that thing is. Does that even matter? Because, I mean, they didn't give us any values, we won't give them any values. What's the big deal? So it's 12 power negative 1/3 times velocity of Earth, that is equal to velocity of Jupiter. And the acceleration of Jupiter, that is just 12 power negative 4/3. That's the velocity of, sorry, the acceleration of Earth. They should be doing it. All right, next question. So 202. Okay, A planet of mass m moves around the sun along an ellipse so that its minimum distance from the sun is equal to small r and maximum distance is equal to capital R. Making use of the Kepler's law, find its period of revolution. We already know what the period of revolution is. It's just this thing. But what is A? So they didn't give us A explicitly. They just told us the minimum distance is small r. The bigger distance, the maximum distance is just capital R. What is A? It's just going to be small r plus capital R upon 2. There we go. Because this is just A times of 1 minus E. That's just A times of 1 plus E. Add them, you get 2A. I think upon 2. Cool. So this is just equal to 2 pi upon, what was this? Square of Tn. Square of Gn. And then you got r plus r upon 2 to the power of 3 upon 2. That should be doing it. Next question. Yeah, that should be doing it. 203. A small body starts falling onto the sun from a distance equal to the radius of the Earth's orbit. The initial velocity of the body is equal to 0 in the heliocentric reference frame. Making use of Kepler's laws, okay. Find how long the body. Oh God, this is weird. But how does Kepler's law? How do we use Kepler's law to the thing? Yeah, that's not nice. Okay, at that point velocity is just 0 and then it's falling. Oh God, what is this? Uh, yeah, I don't know how to do this thing. Think about it. You want to use Kepler's law. So for Kepler's law, you need an elliptical orbit. We know all kinds of motions around the sun would basically be conic sections, right? So can we think of some kind of ellipse that actually corresponds to this thing? Maybe. Okay, what if its velocity was not 0 but very close to 0, right? So almost 0. So what I'm thinking, I know this might sound weird, but think about it. You got this sun, uh, you got, right, whatever the velocity is over here, then like this. So this is the minimum velocity. We are thinking of it tending to 0. Does that make sense? So when does this tend to 0? And the radius, so the R max is just this thing. Okay, so R max is actually a finite quantity. That's yeah, okay, so A times of 1 plus E, that's a finite quantity. So 1 plus E, like it's also a finite quantity. So A is a finite quantity. That makes sense? A is a finite quantity. So sort of Gm upon A is also a finite quantity. So the only way that this actually could be going to 0 is that 1 minus E, that must be going to 0. So E actually should be approaching 1. And that's like kind of like hey, but we know for a parabola, if this is a focus, this other focus would actually go to infinity. So this that's weird. Isn't that weird, huh? But yeah, like E must be approaching 1, if we can even think about it like that. When does E approach 1? Uh, yeah, okay. In that case, B is equal to A times root of 1 E square. That thing approaches 0. So your B value, like if this gets thinner and thinner, so for the same A value, right? If you start decreasing your B value, okay, not the same A value, just the same A times of 1 plus E value, right? Right. So if you start decreasing this value, so A times of 1, you get the idea, right? You will eventually come to this kind of elliptical orbit which has very low V minimum, right? So it's approaching 0, and V maximum is still a finite quantity. Actually, no, it's now infinite because this thing is going to infinity. Yeah, does that really matter? Because it's a limiting case. So no need for worrying. Right, the shape would, oh God, what's that? Alright, the shape would be something like this. A is finite, B is approaching 0. This is how the orbit should look like. Okay, and then what do you want? You want the time, you want its period of revolution around the sun. No, okay, that's 202. You want how long the body will be falling. Okay, okay. But wait, what? So it's got this distance. You want to figure out to cover this distance, how much? Oh, this is weird. Huh. So about that, you can actually figure out what the. This is not helping, is it? It's not helping. It's really not helping because unfortunately we don't know. Wait, actually we do know where it's gonna stop. Yeah, I don't think this was a nice idea. Just do it the usual way. I mean, if the sun was like a point of view, it's gonna make perfect sense, but it's not. So it's not making any sense. Once it enters the surface, right, that's when it has actually fallen. So yeah, that's when you will stop counting time. How long will the body? You don't. How can you use Kepler's law for this? You will have to go for integration. Is there any other way? How do you use Kepler's law for this? You can figure out the half time period or something like that, but how do you use Kepler's law? Maybe this area is like, okay, some kind of fraction of that area, something like that. Maybe it could be. Hmm. How do you figure that out? So you got what the x value should be, right? So, yeah, okay. The x value is like, okay. Think about it. The actual thing is that, yeah, this is how the orbit actually supposed to be. Something like that, okay? And this thing is actually approaching zero. Cool. This is our sun. I mean, sun's center. This whole thing is the surface of the sun. This distance, so almost this is right. That is equal to the radius of Earth because it's that much away from the sun's surface. And this complete thing is the radius of sun. Okay, it's gonna fall like this. So what is this area? Like, okay, this area going to be, right? Exactly. uh Majority of area I think it just comes from this thing. Okay, so you just have to figure out, right? So for that particular x value, what is, you know, the angle? Yeah, basically because this thing is almost the sun's. Okay, this is getting complicated. What if we just figure out the height, right? This is weird. This is really weird. Uh-huh. So for some x value, right? Not, I don't like this. What is this area going to be? How much is this area? For that you will need this and that and that. Okay, that's just not good. Approximately this is our radius of sun. I get that. And what about this small? Do you not take that in? You actually have to because the radius of Earth is not just negligible. You can't just do that, right? You have to take that into account. So there is this area and there's also this area. And if you think about it, isn't this like, okay, this part basically parabolic? Because we know a parabola is just an ellipse, which is very much stretched, and then you're just looking at it from one of the focal points. That makes sense, right? Yeah, actually it does. So this thing is parabolic. Okay. So it's like square root of that, square root of RE. Does that make sense? And we will have to approximate in any case. So, interesting. How do you go from an ellipse? Okay, we don't want to be running into those things. But what other choice do we even have? You will have to do this someday or later. So, right. Just think about it. Maybe we'll come to something. Okay, it's just like parabola and then total area. Just if we could like figure out what the eccentric angle is. Hey, it's not that hard. You can figure out. So let's just write the x value, which is gonna be this thing, so whatever this was, which is a, call this thing a, and we'll just say this RE, right? A minus RE, that's equal to the x value, and that's just equal to what? It is so using that parameterization, it's just equal to a cosine theta, and then y will just be equal to a sine, sorry, b sine theta, right? Yeah, okay, that's nice. Uh, and we know, yeah, actually this thing is just tending to zero, right? Don't worry, we'll do it. And now the thing is like this is very close to this point, so theta is almost zero. You can just write this thing as a minus a theta square upon 2, basically, using the Taylor series. So what do you get? Just get RE is equal to A theta square upon 2. And then this whole thing just turns out to be like B times theta. So what is theta, by the way? Theta is just 2RE upon A, square root of that. So it's just equal to, yeah, okay, you got the thing. You got Y, you also got X. Once you have Y, just do this whole thing. So the R maximum, which is just R of sun plus R, you can do that thing, right? So R sun plus R earth. Okay. Yeah, that would be this thing. Okay. Or, okay, yeah, I mean, instead of that, let's just say this thing is A times of 1 plus E. So write everything using eccentricity. This thing would be written as A times square root of 1 minus E square times theta, right? Perfect. Uh, and, okay, sorry, what was theta once again? Theta was this thing. So it was 2 square root of 2 R E upon A. So, or let's just say 2x upon A. So this is a distance x away from this pole, right? And then you got this thing. So put that in there. Okay, so you got A square root of 1 minus E square. That you have to look for. Am I going correct or not? I think I am. So half base height. I mean, what's theta? Theta is just, you found that the square root of 2x upon A, hopefully. Uh, yeah, I mean, I hope it's going to work out. Okay, that's the area, and you have to divide it by the total area, right? That will, and that times the time period or whatever. So T, and then just do the total area over there. So, or you know what? I mean, once you got the area, just divide by the dA upon dt thing, and then you will find the time required. So divide by L, which, right, we just calculated it the last time. It was like what, half R vector plus B vector, whatever, right? Hey, okay, throughout this the V vector is kind of constant, isn't it? Okay, don't go for that. We'll actually do the thing. So what was the thing? How did we get that? It was like square root of gm times A and then 1 minus E square, right? That was, of course, I could have gone wrong. It has to be the thing. It just has to be the thing. This is B, this thing is something we don't know what that thing actually is. Right. This should work out, most likely. So let's see what happens. I mean, this cancels, and this also cancels. Cool. This square root comes down, just A over here. Okay, perfect. This cancels with that. Awesome. This half cancels. It's got like 1 plus E times A square root of 2x or square root of gm. Now A is just, right, this whole thing. So, and what about this quantity? So that's like 1 minus E. That's approaching 0, right? Yeah, so, wow, this is getting complicated. Okay, calm down. Think about it. A times of 1 plus E, that's equal to this whole thing. That's a finite quantity. Cool. Yeah, A is a finite. No big deal. So as E approaches that, A just approaches, Rs plus Re upon 2. So A is just Rs plus Re upon 2. E is 1. You're gonna put all that stuff in there in the end. But yeah, I mean, this whole thing is just basically Rs plus Re upon 2. So cool. And then you got square root of x upon square root of 2, square root of gn. This should work. So Rs plus, or just call this thing as R max, or the R value that you look for, whatever. Yeah, R max is better. So R max square root of x. Or okay, what about the initial R that you start off with, right? So R naught. That should make sense. So R naught square root of x upon square root of 2gm. And this probably matches up with that formula. Okay, you don't have the 2gm or whatever, but works out, doesn't it? Perfect. Yeah, this is looking good, I guess. Of course, maybe there was some other way to this thing. Yeah, maybe there was. The velocity at that point, okay, that actually changes. You can't just say it's constant. It changes. The acceleration also changes and whatever. Yeah, it's kind of weird. Your RE is very less than our sun. You have to use that approximation to actually think of it as a parabola, because if that's not the case, then how do you think of it? Because it's not, extremely close to the pole. It is close to the pole, not extremely close to the pole. They want us to use Kepler's law. That's why I did this whole thing. I could have just done integration. That would have worked. But there you go. You got the formula. Hopefully, it's gonna work out. Okay, it should work. So this is the time required, huh? Right. In this case, x is just the radius of Earth, and actually R0 is approximately just radius of Sun. So, right. It's yeah, Kepler's law. How does that even work? How did they do Kepler's law to get this thing? You have to go for integration. It's not even whatever. I get it, some kind of limiting case, but it's so hard. It's hard to figure out how that's supposed to be. You actually have to figure out the area for that, right? Your y value. You got this using a parabola, using the fact that theta is very. That's just wrong. That's just wrong. How do you do that? Doesn't make any sense. Whatever. Next. 204. 204 is suppose we have made a model. I mean, you know what? I'm going to do this thing once I've done this video, because surprisingly, this was much harder than what I thought it would be. Right? Okay, 204. Suppose we have made a model of the solar system scaled down in the ratio eta, but of the materials with the same mean density as the actual materials of the planets and the sun. How will the orbital periods of revolution of planetary models change? So, the velocities are just, square root of gm upon a, right? Okay, cm upon r, because circular orbits. Assume these are circular orbits. Okay, you know what? Yeah, just gm upon a is better, because the eccentricities, they won't change because it's scaled down model. If your velocities also get scaled down, then that's perfect, because that will be the scaled down model. You won't have to change the orbital time period in that case, right? That's what I'm thinking. Because if you want to scale down the whole model, you should also scale down the velocities, because yeah, the times should be the same. Otherwise, how does that even work? I mean, I think they want us to assume that velocities are different. We'll see what happens. So V is actually just say proportional to that thing. So basically V is proportional to square root of m upon a, right? But m is proportional to what? Eta cube, right? So it's eta, because it's eta times what it was, right? That's what the radius of the sun will be. So eta cube, that's what m will be. And then this thing is eta and the square root of that. So perfect. It's just equal to eta, as I thought. So the velocity is also scaled down with the same factor. So yeah, like the time period won't change. It remains the same. So the answer would be remains same. Cool. 205. 205 is a double star is a system of two. Okay, we know what a double star is. Find the distance between the components of the double star if its total mass equals m and the time period. So total mass is given and time period of revolution is t. And you want a distance between. I mean, we know it's supposed to be rotating about the center of inertia, but I'm starting to think that maybe let's not do that. Let's instead take the reference frame of this star. So we just say this is a capital M, this thing is small m by mass. I know they're using capital M for the total mass. I'll be using this for this guy, right? Yeah, the distance between them is r. So the acceleration for this guy in the space frame is just g small m upon r squared. This is like g capital M upon r squared. With respect to this guy is actually accelerating by how much? It's this thing plus this guy, right? Because opposite, and you get the thing. So g small m upon r squared, right? Okay, so that's the acceleration, and this is actually just equal to v squared upon r, because this r is supposed to stay constant, right? and its angular velocity is also supposed to stay constant. Actually, you know what? Let's write it as omega square r and not v square upon r. Perfect, because when omega becomes, right, when omega t becomes 2 pi, that's the revolution, right? Yeah. Uh, okay, so what do you got? You got omega square is equal to g capital M plus small m. That's the total mass, right, upon r cubed. So, right, and what do they have? They have the time period is t, and also the total mass is actually m, and not this. You get the thing. So like g m upon r cubed. That's equal to, and omega would just be 2 pi upon capital T, and nothing squared. So 4 pi squared upon t squared. And just solve for r. So r power 3 is equal to gmt square upon 4 pi square. So just want the cube root of that thing. There we go. That's our answer. So this is the cube root of gmt square upon 4 pi square. That should do it. Next question. 206. Is this dimensionally correct? We don't have time to do that stuff. So yeah, next. Come on, why do I want to do this thing? Is this dimensionally correct or not? Ah, okay, so gmm upon r squared, that's the force. So gm is just equal to the force times r squared upon the mass. So kg meter per second square times meter square upon a meter, right? And that times time squared, so you got second square over there. Oh, it's not, it's a mass, sorry. So it's kg. This cancels. M cube works out. Next question. 206. Find the potential energy of gravitational interaction A of two masses of point. Okay, two mass points of masses something something located at a distance r from each other. Of course, that is the usual potential energy. Negative g m. Okay, just say m1 m2 because that's what they are using, right? On r squared. R squared. What am I doing? Okay, and what's b? Of a mass point of mass m and a thin uniform rod of mass capital M and length L, if they are located along a straight line at a distance a from each. Okay, just do this thing. So you got this point, and by potential energy of the actual interaction. Okay, just the interactive energy, not the self energy for this rod. So like if you actually had to assemble the whole rod by bringing in points from infinity, you would also have the self energy of the rod. You don't have that. So just the point mass of small m. You got this rod of capital M, length L, and they are at distance what? A from each other. And what does distance mean? I mean, there are multiple points on this thing. From what point do you want distance? Uh, wow, that's weird. Okay, this would make sense if like A is much bigger than L. That would have made sense, but what if it's not? It could just be comparable to that. Oh god, then how do you get the distance? There are multiple distances that you could have. I think they want distance of their center of masses. What else would they want? Right? Oh god. Or maybe just this thing. So maybe this distance is A and this distance is L, right? That would be the easier case to solve, so I'm gonna solve that case. I don't know whether or not this is A or this thing is A or whatever. They have multiple points on this thing. Which of these do you want? I'll just say the minimum distance. That is small a, right? That's gonna be this thing. Okay. So what do they want? They want the potential. Okay. Uh, yeah, they just want the potential energy. So the thing. So right. Oh god, that's not nice. So you got g m, and then for this guy, just got like lambda dx upon r squared, so a plus x squared, and x is going from 0 to L, whatever, or yeah, just say x squared. So x is going from a to L. Actually it should just be upon x, not x squared, was energy. So, right, and lambda is just a capital M upon L. Don't make extra variables, just use the old variables, right? So you got G M M upon L integration of dx upon x as it goes from a to L, right? A plus L, sorry. So yeah, I guess that should be working out because that looks perfect to me. What would go wrong? What could go wrong? Nothing, right? Uh, yeah, it's all just perfect. There can't be anything that can go wrong. Which is bringing this mass from infinity to this point. It's got to be like that. And of course, negative and whatever, but we'll do that later. Okay, that's the thing. So GMM upon L, and then you got natural log of 1 plus L upon A. There we go. That's the thing. And what? Yeah, that's the potential energy, negative of that, of course. So negative GMM upon L, natural log of 1 plus L upon A. Yep. Okay, and then what do they want? This is what the potential energy. There's also a second part. So uh, then they want, it was like 206, right? Also find the forces of their interaction. Okay, so right, just take the derivative of the thing with respect to A, because as you increase A, your energy, you get the thing. So negative partial 1 partial A. Yeah. So to separate, you have to put in a pulling force. It's gonna work. That's gonna work, of course. That's the thing. That's the force of interaction. GMM upon L, that's a constant. We just want to differentiate this guy. So 1 plus, and then the derivative of this guy, just a negative L upon A squared. Why is that negative? Why is that negative? Uh, is that supposed to be correct? This should not have been negative, right? It should have been positive. So to try to like something's weird about this thing, right? Yeah, as you know, it's like, what is this thing? F dot dA, so F times dA or whatever. So as your A increases, your potential energy is also supposed to increase. So it's equal to the change in potential energy, because it's gonna increase. So yeah, as A increases, this whole thing, right, this value decreases and then negative of that. So right, okay, we put in an extra negative factor that's not supposed to be there. It's just this thing. It's not the potential. It's right. Okay, I'm hitting some other stuff inside it. It's not supposed to be like that. Just this guy. That makes sense. So that's the attractive force. Cool. Uh, yeah, it is going to be like GMM upon L. Take that A down. So you got this thing, then you got L upon A plus L. That should work because perfect. This cancels. So GMM upon A times A plus L. That's the energy. Sorry, that's the force. Okay, is equal to GMM upon A times of A plus L. Next question, 207. 207 is a planet of mass m moves along an ellipse around the sun so that its maximum and minimum distance from the sun are equal to r1, r2. Angular momentum of angular momentum m of this planet is related to the center of sun. Yeah, no big deal. So the angular momentum is just, uh, mr vector cross v vector, whatever, and that thing, just that thing. So right, mr minimum times v maximum, that should work out. So it's like m a times 1 minus e. We already did this kind of calculation before, didn't we? Yeah, square root of gm upon a, 1 plus e upon 1 minus e, whatever. This is just equal to m. Oh, this is by the way capital M. So yeah, square root of gm times a, and then you got 1 minus e squared. Right. And if you think about it, like this is just m square root of gm. So 1 minus e is r minimum upon a, and 1 plus e is just r maximum upon a. So this is actually just r minimum, r maximum, but an extra factor, like it's upon A, and A is just R minimum plus R maximum upon 2. There we go, you got the formula. So let's call this R1 and R2, right? So n square root of gm, yes, 2gm actually. Okay, and then you got this thing. So yeah, you just 1 upon that, the harmonic mean or something. Hey, yeah, like it is the harmonic mean of, oh yeah, perfect. But I'll just write this R1, R2 upon R1 plus R2 because I like it that way. Easier to calculate than the harmonic mean. Yeah, that should work out. So this is our answer, right? That's our angular momentum, the magnitude of that, of course. Okay, 208. Yep, this should work out. 208 is using the conservation laws to demonstrate that the total mechanical energy of the planet of mass m moving around the sun along an ellipse depends only on its semi-major axis. But you want the total mechanical energy of a planet. Huh? Ellipse depends only on its semi-major axis A. Find this energy as a function of A. Oh, okay. So you want the energy, right? Okay, okay, okay. So it doesn't depend on B. That's what you are getting at, right? Okay. I mean, you already got B maximum. Okay, we will also need the R value for this thing actually. Okay, okay, no big deal. That's the thing. So it's negative GMM. I'm finding the energy upon the R minimum value, right? That's when you have the maximum V value, right? That's going to be like 1 minus E times A. And this is half mv squared. So you got 1 upon 2 times mass and then V squared. So why am I even looking? I already have that memorized. So this thing 1 plus E upon 1 minus E. That's the thing. Okay, so take that 8 and you know what? Take some other stuff common. So you got Gm m upon 8 times of 1 minus E. Take that common. So what you got? You got like negative 1. Oh wow, you took everything common. Perfect. Yeah. So you got negative 1 and then you got plus 1 upon 2 of 1 plus E. This thing would just be, you know what? Take that 2 common as well. So you got this 2 out. You got to be that having that thing. So like it's just E minus 1, isn't it? Yeah. So this actually cancels. Just get a negative in the front. There we go, just a negative GMM upon 2A. Wow, that's actually a nice addition to my formula list. So that's perfect. Energy is always just this thing. Isn't that awesome? I mean, this is to be expected, but okay, whatever. This is the thing. So there we go. So GM upon 2A, huh? The total mechanical energy is just negative GMM upon 2A. I want to add this to my list of formula. So that, you know, when time comes, I can actually use this. Because it's so simple, yet it's something that could be asked a lot of times. So, right, energy. So usually I use E for energy, U for potential energy, and K for kinetic energy. Energy is just what? Once again, negative GMM on A. I should actually specify what kind of energy this thing is. So it really is just the total mechanical energy. All right, next. Awesome. Actually, I didn't even know about this formula before this question. Next, 20 what 9? Planet A moves along an elliptical orbit around the sun. At the moment when it was at distance r naught from the sun, its velocity was equal to v naught. Okay, and the angle between the radius vector r naught and the velocity vector v naught was equal to alpha. Why does this look like a okay? Okay, interesting. Find the maximum and minimum distances that will separate the planet from the sun during its orbital motion. Interesting. That angle was alpha. They gives the velocity, they gives the radius, and they gives alpha. Okay, you can figure out the angular momentum through this thing. Cool. And you just want the minimum and maximum distances, right? Okay. I mean, you already got the angular momentum in terms of minimum and maximum distances. Also the energy, I guess you can figure that out as well, right? That's one thing you can do. So you can get A from that directly without having to do anything. Perfect. Right, so just using these two equations, you can actually figure out R1 and R2. But that's just a big, yeah, it's just a bunch of calculation. How am I supposed to do that actually? Oh, it's gonna take forever like this. Yeah, it's going to take forever. Oh God. Uh, yeah, it is going to take forever. How do I do this thing? Well, there's no other way. Just start doing it. Okay, fine. So the angular momentum is just equal to m v naught r naught times sine of alpha because cross product, right? So right, of course. So v naught r naught sine alpha, that's just equal to this. M is not going to survive, so right, just square root of gm, and then you got just say 2 gm. Does that really matter? Square root of 2 gm upon square root of 1 upon r1 plus 1 upon r2, right? Yeah, and also the total mechanical energy. So 2a is just r1 plus r2. So that is awesome, I guess. And that just means like negative gm upon, so I'm skipping the small m value, that upon 2a, that is r1 plus r2. That is equal to what? Where did that go? Uh, where did that go? Right, the total mechanical energy. This is equal to half m v naught squared, so m is gone, just v naught squared upon 2 minus gm upon r naught, right? So once you know these, you're good to go, right? And using these, we want to figure out what r1, r2 is and everything. Yeah, it's kind of a hard thing to do. Hmm. Okay, think about it. How do we go ahead and do it? Uh, I think the previous one was actually better. Write it like not like this, but like this sort of r1, r2 upon r1 plus r2, right? That was better. Yeah, because you already got this thing. So just gotta take the square root, and that will actually gives the r1, r2, or square that. Square that. That's the better thing to. So you got r1, r2 upon r1 plus r2. That's just equal to v naught square r naught square sine squared alpha upon 2gn. Cool. And of course 1 upon r1 plus r2, that's just equal to 1 upon r naught minus v naught squared upon 2gn. Awesome. Right, so just dividing, you will get r1 r2 like that. So r1 times r2, that's just equal to, yeah, I get what's happening. I just don't like the way it is, right? Yeah, I definitely don't like it. Or you could divide it by that. I don't like the way. Some other way to do this thing? No, nothing. Wow, that was not nice. Uh, how am I supposed to do this thing? I mean, I get it. I can easily figure out R1, R2 by forming a quadratic equation, but it's gonna take forever. Let's call this thing as A for now, and this thing as B. But you know what? No, let's actually divide first, and then we'll figure out the stuff later. Yeah. Or even writing this in terms of 1 upon R was better, because right, okay, if let's say 1 upon r1 is equal to x1, so this would be written as x1 x2 upon x1 plus x2, right? This stuff. Sorry. And this thing would just be 1 upon x1 plus x2, right? That is equal to 2gm upon, oh, sorry, just this thing, sorry. V naught squared r naught squared sine squared alpha upon 2g. You get the thing. And this will just be equal to whatever this thing is. You just divide by that. That's much better than doing this, right? And that we can get, but you will have to take the reciprocal in any case. So what's the point of doing? Other than solving these quadratic equations, is there any way to get this directly? Unfortunately, there isn't. Yeah, there isn't. There isn't a way. And think about it. You can't just divide. Oh, that's not helpful. It's still the same equation. It's degree 2 equation with all of that messed up stuff. Better not do this and just do your work. So divide without caring on anything. So v naught squared r naught squared sine squared alpha upon, just multiply by 2gm. So you're gonna have 2gm upon r naught minus v naught squared, right? This thing can be written as v naught squared r naught cubed sine squared alpha upon 2gm minus v naught squared r naught, right? That is what r1 r2 is, and then r1 plus r2 is just, how do you get r1 and r2 by themselves, not like this? You won't get it like that. Oh god, you will have to invert this. Are you serious? Why? So you got 2gm r naught upon 2gm. This is not helpful. Minus v naught squared r naught, whatever. Okay, now think about it. How do I get this thing? Uh, it's not even the denominator is not even the same. How am I supposed to get anything out of it? It's impossible. Yeah, okay, that's where I'm stuck. I don't know how to proceed after this thing. You will actually have to solve this equation, and that is, yeah, I'm not into doing that. Right, just gonna leave it like that. Okay, so I'll just say E is equal to v naught squared r naught cube sine squared alpha. You could have just guessed a solution, but that's not possible because of this bad denominator value, because these are the same. So yeah, it's impossible to guess anything in that case. 1 2gm. Maybe you could, okay, just multiply this thing by, no, that's not going to work. It's not going to work. Why is nothing working? Okay, just keep on going. Minus v naught squared r naught, and then a is this stuff, so 2gm r naught upon 2gm minus v naught squared r naught, and then you know the thing, r1 2 is just equal to minus b, so you got minus, yeah, a is some sort of b squared minus 4c, so you got a squared minus 4b upon 2. That's right, that's where it stops, huh? Perfect. Or you could, okay, you know what, simplify a bit, just a bit, call this thing a, then this actually can be written as, just negative a plus or minus square root of a square minus b, right? That's better than that at least. So that's what r12 is, right? These are the, so the r max is just equal to, and these are like, okay, negative or, oh shit, one of them is negative. Why is that the case? Oh, it's supposed to be negative of that. Okay, sorry. Um, right. It's actually supposed to be positive in that case. Yeah. R max is just this thing plus that thing, and then R min is a minus square root of e square minus b. Still just that much problematic. Not gonna help. I wish it could have helped. Uh, if we have any chance of helping, we should actually write b as, yeah, having a square of this guy in the denominator. I doubt that's even useful. We got v naught square r, huh? So v power 4. Hey, why is that ringing a bell suddenly? And you got 2gm, so 2gm v naught square r naught cube sine. That's fine. Then for a square, we just have g square m. Okay, that's not helping. Yep, that's where it stops. It doesn't help anymore. Fine, whatever. Next question. 2010. A cosmic body A moves to the sun with a velocity v naught when far from the sun and aiming parameter L. What? The arm of the vector v naught related to the center of sun. What? Figure 1.51. Okay, so this is a cosmic body A. It moves to the sun. Where is the sun? Velocity v naught when far from the sun. So it's far, fine. Uh, right. And aiming parameter L, the arm of vector v naught related to the center of sun. Okay, right. Find the minimum distance by which the body will get to the sun. So basically they give us the angular momentum, right? Because they give us L, and yeah, that just gives us the angular momentum. Cool. And when it's far, whoa, that's not an elliptical orbit. It's like some kind of parabolic orbit, because or hyperbolic or whatever. Oh, that's interesting. Fine, they give us the angular momentum. Uh, and what do you want? Find the minimum distance by which the, so dr upon dt equal to 0, so the velocity is completely in the tangential direction for that to happen. Right. And r should be minimum. In that case, your velocity should be maximum, right? Because, of course, whenever r is minimum, your speed is maximum, energy conservation. So at this point, is tangential, velocity is maximum, r is minimum. Yeah. And the angular momentum is still the same. So, huh. Well, what would you say? I omega is still the same. It's planar motion, I can do that. So I omega is still the same. It's like, think about it. I omega square upon, okay, square root of I omega square times I is, so square root of k times I is the same. Okay, the energy, you don't want to be doing it like that. You want maximum what? The maximum velocity, right? That's getting weird. Okay, whatever. So you just want like v cross r that is conserved and whatever. The kinetic is also conserved. You will actually have this thing. There's no escaping it. I don't like it. I don't like the way it feels. We know it's parabolic or something like that. Hey, you know what? No, it's not parabolic. It's actually asymptote. Yeah, this kind of a, because it's far away. It's an asymptote over here. It's a hyperbolic motion. Ooh, that is not nice because we have not studied that. So I have no idea how to do that instantly. We'll have to go for basics in that case. So, right, okay, whatever is the velocity at that point, we just say it's v and that times r. So r is, at this point, right? That's just equal to v naught times L naught. So L, yeah, that works. And also you got half m v naught squared. That was this energy initially, and its potential energy was like 0, whatever. That's equal to half m v square minus gmm upon r, right? So what do we have? We just have v square is equal to, that is just 2, so 2gm upon r and plus v naught square. So, okay, that's awesome. Your v times r is equal to this stuff. You could just square this thing, right? Or even better, just put v as this thing upon r. So this will just become v naught squared L squared upon r squared is equal to 2gm upon r plus v naught squared. And then you got an equation in 1 upon r. That's just a quadratic. Perfect. Isn't that right? Okay, cool. Divide by v naught squared, of course. So L squared upon r squared minus 2gm upon r squared times 1 upon r. Okay, not plus 1 of minus 1 is equal to 0, right? Yeah, interesting. This thing can be thought of, oh, it's just not r squared, it's like v naught squared, sorry. Just multiply by r squared actually. So you got r squared plus 2gm upon v naught squared times r. You got this stuff, so minus L squared is equal to 0. And now just have to solve for r and get the value. And you also want the minimum value, so you know the smaller value. So you got minus b and all that stuff, right? You got, just say this thing is what we call as capital B, so just minus 2b plus minus square root of b square is just 4b, right? Minus 4 is, you got just 4L squared and nothing upon 2a, right? So a is 1 minus b. Yeah, this should work out, no big deal, right? And another value is somehow negative, which I think it does make sense. I mean, there is no maximum value. This right? Okay, that maximum value that we are thinking of, it never happens. It's at infinity or something, whatever. So you got negative b plus square root of b square plus L square. Now b is just that guy, so it's negative g upon b naught square plus square root of this thing square. So you got g square m squared upon b naught squared. And then yeah, all we have to figure out is minimum r, right? Where did that question go? Uh, okay, one second, where did the question go? Minimum distance, of course. So there we go. This should work out. Okay, plus L squared. That's it. That is our formula. That's why I don't like using basic principles for this particular topic, because those are just insanely hard to use. You instead have to rely on these things to get your thing done. 211. Okay, a particle of mass m is located outside a uniform sphere of mass capital M and distance r from its center. Find the potential energy of the gravitational interaction of the particles. That's easy. So just negative gmm upon r. No big deal, right? Yeah. Okay. I mean, we have to show that, but I'm not going to do that. That's an exercise for you, right? You know, like use whatever you want, Gauss's law or anything. The gravitational force which the sphere exerts on the particle, that's just equal to g upon r squared. Why are they asking us this thing? Isn't that so fundamental to whatever we are doing right now? Outside, right? That means this thing. Cool. Next. All right. So 212. Demonstrate the gravitational force acting on a particle A inside a uniform spherical layer of matter is equal to 0. So gravitational force, right? Yeah, okay. So by radial symmetry, the force is always either pointing out or in. It can't be pointing like in some random direction. How would that work, right? Yeah, okay. So by symmetry, it should just be pointing radially. That's our big assumption that we make. I don't like this kind of proof, but yeah, right. Was there some other better way to do this thing? Hmm. Gravitational force acting on a particle inside a uniform spherical layer of matter is equal to 0. We could try to do a surface integral. That's another way of doing it. So we know it's completely in the x direction because the gravitational force because of this kind of ring. So you got whatever kind of body this is, right? It's a sphere, we know that. And you got this strip. We know that the gravitational force because of that is only in the x direction. That is an easy calculation. You can do that by yourself. So what we can conclude is that the force on this particle is completely in the x direction. So yeah, it's completely in the x direction. You don't have to look for anything else. Okay, that's awesome. So okay, now think about it. How do we do this thing? So for a surface area dA, right? So it's dA vector pointing like this, whatever. Yeah, it's crazy. It's really crazy. It's like nothing upon r squared or something like that. It's like g, whatever the surface density is, times GA. So GM upon R. You just want the field, the acceleration, or the force. You get the thing. That M will cancel out. Yeah, I don't have to explain. And this thing upon this is R, that thing square, but it's along a direction, so it's along the R hat direction. You could have negative or whatever, we don't care about that. Right? Okay. That's how the force is supposed to be. And we just want to integrate this thing. Cool. So dA is not actually pointing towards R hat, right? Hey, I think we have done this integral 1,000 times, maybe. No, no, it's yeah, we did this integral for a disk, not for a solid sphere, because right, for a solid sphere it's not, you can't do it like that. Okay. Uh, A and then R hat. You only want the x component in any case, right? So the x component of R hat, that should work. Okay, so x component of R hat is like taking the dot product with I hat, right? A vector is not completely in the I hat direction. You can't do A dot, so A vector dot R hat. I was thinking you could somehow use a solid angle or something like that to get this thing done. You can't. That's not a correct thing. Yeah, the easiest thing to do is just use Gauss law and assume radial symmetry. So then the field is completely in this direction, right, in the radial direction, right, throughout this surface, and then it's very easy to figure out that it's going to be zero because the matter enclosed is zero, right? This is a like that's the way it's taught in electrostatics. Yeah, I do want to actually do this a bit more correctly, not just using assumptions, but how? Do we actually have to integrate? No, I don't want to be doing that. Integrating this thing is just a painful thing to do. You could do this thing like, okay, just start off at these disks, sorry, at these strips, figure out how they exert a field, and then integrate, and then you get the thing. But it's just redundant because we know it's going to be zero. Isn't there some better way to prove it's zero without having to go through all that? No, why? Oh God, this isn't looking nice. Just want the x component. Hmm. Come on, think. R squared. Only the x component. Ah, this is awful. It won't help. Yeah, now what do I do? I'm stuck. You could just do, okay, dAx vector and that dot r hat, right? Interesting. So you got r hat. Okay, that's weird. What's that making sense? Uh, Fine. I mean, that's one way to be thinking about it. That only the x component of our area, we could just talk about that and then dot r. Am I going correct in what I'm doing right now? I have no idea. Yeah, then basically what I'm doing is like making this whole thing actually become something like a disk or not exactly. That doesn't work like that. Uh, yeah, to get the solid angle, you would need. It's not gonna work. It's not gonna work. You don't have a nice property for this. It doesn't work like that. Or if I did put the others like yeah, okay, the whole dA vector that thing can thought of as like okay dAx and then plus some other component, right? And that property is actually constant as we go around this loop. And, that doesn't equal to zero. That's just yeah, there's no way to do this thing. So fine, just move on. We already know that it's zero. Do we really have to prove this through basic integration? No. So I just leave this 213. Okay, a particle of mass m was transferred from center of the base of a uniform hemisphere of mass m and radius r into infinity. So you got a particle of mass small m transferred from the center of the base of a uniform hemisphere of mass. Wait a second, that's potential. Hey, so if we could like prove that the potential inside that okay, inside that spherical shell is actually the same, you are done basically, right? That's interesting. The potential, and that's a scalar, so you just add it up without having to worrying about vectors. So that would be like the surface integral. You got dA times sigma, but also the g stuff. So g sigma dA, that's gm, and then upon r, basically, right? So upon r, yeah, that's really weird. Oh god, right, that didn't help much. uh, oh god, that doesn't help. dA upon r. Sorry. Uh, it's not even a component or anything like that. It's just R. Yeah, just R. Nothing else. Come on, think. What can we do about it? You want to find this potential somehow without going through the two-dimensional integration, the two variable integration. So, is there no way to do this thing? Okay, maybe dA can be written in some other way. So, it's kind of like it's almost spherical, but not exactly. Or it's also very weird. Mm, yeah, I don't know. I don't know how to proceed. Other than Gauss's law, how do you do this thing? How do you prove that potential is actually constant? You will have to figure out this integration. I get it, but how? Right? Uh, I really don't understand this thing. Right? And yeah, like the potential increase as you increase your distance a bit from the center. It's the same. By symmetry, you can definitely do it, but I want a better way. Something that doesn't rely on symmetry. Okay, if there was a better way, then we would have used that into multiple scenarios, and then you wouldn't actually have to integrate for each scenario individually. So the conclusion is there is no better way. We are stuck. There's no escaping the fact that there is no better way. You just have to rely on these things. So you got this spherical surface, right? Yeah, okay, the same uniform mass density, areal mass density. As you move like this, so as you move tangentially, so this point and this point, all these points actually have the same potential. So this field in this direction has to be zero. right? So this like this whole sphere is actually an equipotential surface, right? Yeah, and this whole sphere is also an equipotential surface. So going from this point to that point, whatever the potential change you have, it's the same potential change over here. So the field is completely in the radial direction, right? So it's always pointing like this. That's how the field is pointing, the gravitational field, by the way. So then you can just use Gauss's law and get the thing done, right? Yeah. So what was this thing? It was just G rho. Wait, it's getting weird. Gauss's law. It was G sigma in this case because surface density, right? I mean, and then the solid angle, of course. That was the flux, and that's just equal to the field, which is basically the acceleration or whatever. Yeah, yeah, whatever. Right, right. Uh, the field is pointing. So the field which says G vector, so it's equal to integration of G vector dot dA. Why did we have to use this? Okay, dA vector. Wow, this is bad. Uh, yeah, awesome. Right. What was this thing? It was this, right? So for electrostatics, it was what was the thing? It was like Q upon epsilon naught for a whole sphere. Basically, it was like Q upon 4 pi epsilon naught times 4 pi, right? And then you also got like K over there. So yeah, right. KQ sigma. That's what I used to do. Uh, sorry. This thing by itself was K. Why am I doing this extra stuff? Right, this was actually K, so KQ and then sigma, that was the thing. And similarly for this you could just prove it's actually G, the mass enclosed inside, right? So not sigma, it's just a GM, and then solid angle, right? So GM solid angle, the mass enclosed inside is 0, so this thing is actually 0. Solid angle was 4 pi, doesn't really matter, and there we go. And then G vector dot d vector, that's the same thing as G dot d, right? So G times d, because scalars, and G is constant, radial symmetry, so you can take that out, and then integration of that thing is just the area, which is 4 pi. What does that prove? 4 pi, that's r squared, of course. What does that prove? That just proves that G is equal to 0. So on this point, the gravitational field is 0. There we go. That's the way that we actually prove this thing using symmetry arguments, right? The easier way. And there's other way, which is through actual integration. I don't want to be doing that. Anyway, next question. 212 is done, right? Just put a correct over here. Not quite, you know, not the kind of question that I was looking for, but whatever. 213. A particle of mass m was transferred from the center of the base of a uniform hemisphere of mass capital M and radius r into infinity. What work was performed in the process by the gravitational field exerted by the particle on the particle by the hemisphere? So you got a particle. Yeah, just okay, just find the potential it initially was. No big deal. So for a full sphere, a full solid sphere, the potential is given by 3 upon negative 3 upon 2, granted, GMM, because that 1 upon 2 factor comes, you get the thing, no big deal. And then upon R, and that's a potential energy, right? For negative. That is for, so that's the interactive potential energy of this mass small m and the whole sphere. But now it's got a hemisphere, so actually it's going to be like negative 3/4 of that. Because, yeah, it's a summation of G m upon R I sum, right? Actually, I should say G T M whatever R I. Yeah, okay, the integration of it. You get the thing, the volume integral, right? It's just basically this thing, that's the potential. So it's just exactly half of that. And this is right, this potential energy, you are right, that's the work done in moving this from that point to infinity. by us, right? This is the work done by us. By the gravity, it is this thing. So yeah, right. That's the work done. Any change in kinetic energy? No. So that is the work done. It's a stationary particle throughout. Next question. 2014. Sorry, 214. Right. There is a uniform sphere of mass m and radius r. Find the strength g and the potential rho. Sorry, no, potential phi, whatever, of the gravitational field of this sphere as a function of the distance r from its center with r less than. Ah, come on, that's just a classic question. Do I have to do this thing? Draw the approximate plots of the functions g of r and phi of r. So g is what? The strength of the field. So it's small g, that's what we should say. Right? G is equal to gm upon r squared when r is bigger than capital R, and g is equal to, so right, it's actually linear related to r. So gm upon capital R squared was the field at the surface, now r upon r of that thing. So basically gm small r upon capital R cubed. That is when r is less than r. No big deal. And what else are they asking? And also phi of r, which is the potential. So phi when it's, yeah, away, so it's like gm. Do I really have to do this thing? Why am I doing this thing? Right? Yeah, 2014, it's 214. I can do this at the time when I'm asked this question. I'll just say, yeah, done. I won't even draw a plot or anything. 215. Inside a uniform sphere of density rho, there is a spherical cavity whose center is at distance L from the center of. Have I seen this question many times before? Yes, I have seen this question. So you got a uniform sphere, you got what? Spherical cavity, uh, whose center is at distance L from the center of the sphere. Okay, cool. L, whatever. Find the strength G of the gravitational field inside the cavity. So you can think of this cavity as negative mass, right? So you got this complete guy. Uh, yeah, what is the thing? Once again, just g m upon r squared. So g, and what's this m? It's like 4/3 pi r cubed times density is given, right? That's perfect. Times rho, right, upon r. And you just want the field, you don't want the force. So, right. So 4/3 pi g rho times r. Yeah, that is the thing. Okay, and r actually, you should actually say it's negative r vector. So r vector is the point going from this to that or something like that. Whatever, whatever. Does that really matter all that much? It doesn't, right? Yeah. So, right, it's like this is what we're calling as, let's just say capital R vector. Nah, R1 vector. So let's draw it better this time. This vector going from here to here is L vector, or actually, yeah, just L vector, not L vector. What am I doing? And then this vector is R1 vector, and this vector is R2 vector. So because of this bigger sphere, the field is just this thing. So R1 vector is pointing in that direction, whatever. Because of this negative mass sphere, it is going to be just a negative 4/3 pi g rho. So rho basically becomes negative rho. And then you got R2 vector. Right, and this is basically just 4/3 pi g rho. R1 vector is this point, R2 vector is this point with respect to this guy, right? So this thing minus that, just this vector, which is L vector. There we go. That's the thing. So L vector is just pointing in that direction. So it's going from the cavity center to the center of the sphere. Okay, cool. L vector goes from cavities center. Am I writing this down? Uh, to actual center, and then you can just do this thing. So and then the field is just this guy, 4/3 g pi rho L vector. There we go. Next question. 216. 216 is a uniform sphere has a mass m, radius r. Find the pressure P inside the sphere caused by the gravitational compression as a function of distance r from its center. Evaluate P at the center of the Earth, assuming it to be a uniform sphere. What? So it's a solid sphere. Okay. Pressure inside the sphere. Ooh, that's okay. So it's radially symmetric. We can assume that much at least. Right. Okay, I understand what's happening. Just it's like hard to understand what exactly. Okay, okay. You could probably use energy conservation or something like that, right? So yeah, okay. So what we could do is, since right, so I'm thinking of this thing. You got this big solid sphere. I'm going to carve out all of this mass, right? So I'll first of all, right, carve out this mass, like make a cavity or something, and then I'll put all of that mass onto this small blob at the center. So the field experienced by all of these points on this, right, this shell, same, right? It's still the same field, same orient, right? The same kind of arrangement and everything. This is still the same field, the same forces, and just the thing is, we are artificially keeping this surface over here. So we have installed the surface and this kind of weird, very dense ball, right? Okay. And then what we are thinking is, so we will need some force to be right. So with some pressure on this surface to keep these blocks from falling inside, right? Yeah. Okay, so that pressure is P, and it's the same throughout because radial symmetry and everything. So now what we are thinking is, and I just assume like this thing is fluid or whatever. I know it's not correct to do that, but assume it's fluid. Does that really matter all that much? Okay. And then what you're thinking is, if you actually, okay, now I'm just out of words. I don't know what to say. Oh, really? Oh, come on. Okay, that's not helping. Ah, I want to explain how this is going to. So what I was thinking is that if you increased this guy's radius, so you pushed it out with the same pressure, then PdV is the work done by you, and that's the change in the gravitational potential energy of this whole system, right? That's basically the thing. Yeah, but then I realized, okay, the gravitational potential energy is gonna change in a very weird fashion because this whole thing will have its volume changing. Okay, that's just not good. Basically, that's not good. I can't do it that way. Okay, so something else. Maybe a bit of differential equations would work. What's happening? Was that? Okay, whatever. So differential equations, maybe. You got this piece uh, over here. It's at distance r. You got some pressure difference because of that thing, and then right, some pressure difference along these. And these are supposed to be the same, right? Yeah, these pressure differences are the same because radial symmetry, right? So also these pressure differences are the same. So there's only these pressure differences that you have to make different because these are different. Yeah, and what kind of forces are there? There are these two pressures, so forces because of that, and then there's gravitational force on this because of the whole interaction with this big sphere. That makes sense, right? So, okay, not even a difference. That was actually much easier than what I expected. This is actually doable. Once you realize that these two pressures will be the same, it's actually doable. Wow. And what shape is this thing? So this was like, okay, a big spherical shell, and then you carved out a solid angle from the spherical shell. So right, what piece you got is just that portion. That makes sense. Okay, right. And of course, right, it still is a differential equation. It still is a differential equation. It's not over yet, right? So you got solid angle rho, that times r squared, and that times p. That is the pressure because of that. And this new thing, it's going to be rho, and then you got r plus dr square, and then p plus dp. Well, I should say p minus dp. Does that really matter? No. dp is negative. Just make that happen. So this is the, yeah, that's the force pushing it down. Actually, we should push it up. So it's going to be negative of this guy and plus of that, right? That's the force pushing it up because of the pressures. And that's equal to the actual gravity force on this guy. This is weird. Did we really have to do this thing? I don't know. That's equal to Gm. So you want dm, and for that you will need the volume of this thing, which is so sigma r, whatever this symbol is. Okay, whatever. R squared. What is this symbol called? I don't know. Yeah, whatever. Okay, so solid angle times r squared, that's this area, right? And then this times dr, that is the volume. So this times the density, right? And all of that upon r squared once again. So that would be the gravitational force. There we go. Oh, okay, that's the problem because this m thing is actually not supposed to be this guy. It's supposed to be. Oh, okay, everything is going wrong actually. This is problematic because so before removing this, right, you had this whole spherical shell. The field because of that was zero in regions like these, right? But now that we have removed this, oh, that's not nice. But hey, still assume that to be zero because what we can do is just make this very thin, dr, right? So this whole thing, it will not actually put any significant field, only this much. That's what we have to care about. So in this case, instead of m, you actually have to use the density and everything. So you got, right. Oh, you will need density square in that case. See, it just it just transformed from a problem that can be done on a test to a problem that cannot be done on a test. So you got 4/3 pi r cubed times rho, actually squared in this case, sigma dr. Is this sigma? I don't know. And this cancels because areas are cool. At least that works out. Uh, okay. Hopefully this will work. Right. That's equal to this thing. So let's see what happens. Now, this difference on the left hand side is just the differential of this whole thing. Wouldn't you agree? Except that sigma doesn't, okay, this solid angle doesn't really change. So, solid angle and then the differential of this guy, which is, yeah, just write it as dr squared p. Don't worry all that much about it. Right. It should actually be negative of this thing because, yeah, right. So this pressure must be higher, and that's why. Perfect. Okay, perfect. So this cancels. We just got this as thing, and through this you can figure out the pressure, hopefully. So r squared p, the differential of that thing, and then what else do you have? You have r cubed. That's completely in terms of r. Isn't that nice? So yeah, just integrate right away without caring about anything. So it's like delta r squared p. So here the pressure is something. Here the pressure is zero, or the atmospheric pressure, or whatever you want. Wow, this is going to be. Uh, hey, okay. At this point, r squared is zero, right? So yeah, you could use that fact. R squared is zero. Interesting. So just dp squared. Okay, cool. As you say. So dr squared p, that is zero over there. So like this guy. Cool. So just got r squared p. That works out. That works out at that particular point. Cool. And that's equal to the integration of this whole stuff. I'm getting a bad feeling about this thing because how do we know that the pressure over here is finite? What if it's not? What if it isn't finite? What if it's infinite? Then that's a problem, isn't it? Yeah, okay, this could go wrong. Distance apart from the center. Yes, but oh, so at the center of Earth, assuming to be uniform. Okay, this is very weird. Whatever. But why is this negative stuff over here? It's not making sense anymore. The r square p value that should be high when you are down, right? When you are low, it should actually have a bigger value, and then it should be a smaller value as you move up, right? But what that would mean is, but at r equal to 0, you will just have, oh, this doesn't help. How could it be negative? That doesn't make any sense, right? It should be opposing this gravity, so it should be higher over here, and which would mean that it's the highest at the central point. That's when the r square p value is the highest. But that's clearly not happening because you're getting r equal to 0. So the only way for this to actually happen is that pressure should approach infinity. Doesn't make any sense. How can that happen? The pressure approaching infinity? But then we actually have to figure out the pressure at the center of the Earth, assuming to be uniform sphere. What? Then something went wrong, right? Something went wrong, of course. Uh, what went wrong? Sigma r square p, that's just the force, because this is the area that has the pressure, that's the force in the radial direction. And then what this guy, which is also just that much, right? Yeah. Uh, you also got these other forces from the surrounding. Do you actually have to take those into account? Because, oh, you do have to take those into account because those matter as well. Okay, those actually matter because of the solid angle, right? But then as the solid angle approaches 0, you could get rid of those things, right? It's not helping. It's not helping. Yeah, you don't want to include solid angle there. That won't help, right? What's going wrong? Something's not going correct over here. Oh God. These forces, right? Even though they are the same, they could actually produce something that's right, a kind of force that is not working like that. And it does depend on sigma or whatever this angle is, right? The solid angle. So maybe you do have to take those into account as well. So you got the same pressure on every single place, right? And then these combine. Oh God, oh God, no, 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 this is not nice. The problem is, so you got this block, and just it's a slice of, you will figure out what that thing is later on. It's a slice like this, and right, it's not helping. It's not helping. Shit. I thought this would work out, but for some reason, I missed a factor. I missed this thing. This angle is not 0. You can't just say that these are the same forces. They are the same pressures and whatever. Their magnitudes are the same, but they are not in the same direction. They are in slightly different directions, right? So if this angle is like theta, you got the force PDA from here. I'll just say DF, right? So you got this force, or okay, that area is actually small. Wait, what? But theta is also small, so we want a first degree approximation. It's going to be small, so we can actually cancel those away. This is not helping me. Come on, help me. You don't want two differentials at the same time. But then, how does this equation make sense? It's saying, what is this? dr square p is equal to this guy. This is the gravity force that you're putting in. Alright. dr square p, you're saying, the r is increasing or whatever. Doesn't really matter. We got this stuff. No, the pressure cannot be zero. That is wrong. This is wrong. Right, that's it. I'm not understanding anything now. How do we proceed? This is weird. How do we proceed? You do have to take this r squared into account. You can't just forget about that. You have to take it into account. Like the areas on which this pressure is acting, those are different, right? Slightly different, I get it, but those are different. You can't just neglect that. Or can you? What if you actually open this? You just have 2r p dr and then you got r squared dp and not helping. It's not helping. Okay, I think you should stop now. I'll see you in the next video. Bye.